In this part, we'll be looking at non-traditional schedulers. Let's basically the schedulers that we have seen in the previous lectures are more traditional schedulers, whereas there are other types of schedulers which are very specific to different scenarios. So let's look at those schedulers. So, and another way to look at fairness in process schedulers is the CPU time, right? So we want to make sure that all the processes get their fair share of CPU. Okay, and here we don't have any specific goals such as uh, we are not interested in minimal turnaround time or minimal response time, but all we want to make sure is every process gets corresponding share of CPU. Okay, none of the process is starved. Okay, so how to share CPU proportionally? One obvious idea is to use probabilities. So there is a scheduling policy called lottery scheduling. It's not exactly policy; it's kind of mechanism, but you can see it both as a policy or a mechanism as well. So we know that shortest job first has minimal turnaround time, but it's unfair because now the longest job, like the job with more that needs more time, may never get to run. And we also know that priority scheduling is good, but priority scheduling, the way we modify priorities is kind of ad hoc, in the sense we don't know, like in order to change priorities for certain class we need to do something. So there is no principled way in which we can change the priorities of all the processes for all the possible use cases, right? So based on these two observations, researchers proposed scheduling mechanism called lottery scheduling. This is a research paper that got published in OSDI. So OSDI is a name of the conference called Operating System Design and Implementation. So here they propose this scheduling mechanism. Here the thing is based on lotteries. So we know that the basic principle of lottery is everybody gets a ticket, and we randomly pick a ticket which whoever owns the ticket wins the lottery prize. This is exactly the principle here. So here what happens is each job will get certain number of tickets. Okay, and every time we have to schedule, we randomly pick a ticket. Okay, and any process that has the winning ticket gets the chance to schedule. Now you can see that the jobs that have more tickets have higher probability to win, right? So this gives very nice mechanism to to implement various kind of scheduling policies. For instance, for to implement priority scheduling, just give the highest priority jobs more tickets, right? And to approximate shortest remaining time completion first scheduling policy, we just give shortest jobs more tickets. And to avoid starvation, let's make sure that every process, every job has a ticket. So this gives very nice way uh, to achieve fairness. At the same time, it can we can implement various other scheduling policies by using this. Although it doesn't give any guarantees, but uh, when you read the paper, they show in the evaluation that most of the times it performs what we want. Okay. And one important thing about this scheduling mechanism is it's very easy to implement. So as you can imagine, it's just like every scheduling decision. We don't need to traverse through the queue. We don't need to like pick the process. Know the we just pick a lottery and see which process has the lottery. That's it. So it's very easy to implement. So there is another type of scheduling called real-time scheduling. So most of the times uh, we may have certain hard constraints on the jobs that we want to run. So these could be hard deadlines. For instance, uh, let's say in case of a system that controls like the power for the entire city. Okay, so we may want to, if we run a job on the power grid, we may want to make sure that any submitted job completes within certain time, or else the city may be out of power. Okay, so this is a hard deadline. So we have certain deadline, or rather certain constraint on each job that we submit. Similarly, we can have jobs of soft deadline. For instance, let's say when I send a mail from uh, mail when I send a post to Piazza, I still have some deadline, but it's kind of a soft deadline. I want to make sure that when I post a response, that's immediately available. At the same time, there is no strict deadline, but I want to make sure that my comment is posted most of the times on time. So now the scheduling can be decided on the real-time constraints of different jobs, and this provides user control. Right now, user can be assured that any constraint, for instance, any hard constraints placed on the job, is satisfied, and user gets nice control on the jobs that run on the system. Okay. And it's deterministic, because we know that all the jobs will be completed at certain time, so we can predict the behavior of the system. Okay. And finally, it's responsive, because we can always we know that operating system will definitely finish given jobs within the deadline, so we know that the system is responsive. So real-time scheduling provides these nice characteristics. However, it needs to, one disadvantage is that we need to be able to say the real-time constraints for each process. Okay. So that's why this is not used in like regular user mode systems, but they are used in real-time systems, such as like power grid controller or some IoT devices, where there are certain real-time constraints on the jobs that run on that system. In the similar lines, another type of scheduler is deadline scheduler. So here we can have deadline for different phases of each job. Okay, when we submit a process, we can have a deadline for its starting time, we can have a deadline for its completion time. We can, that way, whenever we submit a job, we give all the information of the job to the operating system. So operating system might take the job or reject the job based on whether all the given deadlines can be met or not. Okay, so this is called admission control. So in case of deadline scheduling, we create this template for the process, where the template contains the deadline for the starting time, deadline for the running time, deadline for the completion time, and how much time is needed for processing, and what are its resource requirements, and what are priorities, and does it have any threads or not. So once we give all this information about a process, operating system might take the process or reject the process. That is admission control. So the decision is based on whether those deadlines can be met or not. Okay. So once a process is in the system, then the scheduler can decide which process to schedule based on the deadlines. So basically, the one thing it ensures is all the deadlines are met. That's it. So the way it schedules depends on the deadlines and depends on the configuration of the system. So, and all the scheduling algorithms that we have seen till now are under the assumption that we have only one CPU and we have only one user, right? However, on real systems are multi-processor systems, where we have multiple CPUs with their own caches and a common memory, and where we have a single operating system that runs, like, that controls all the entire system. And we can also have cluster, where we have different machines, each running their own copy of the operating system, and they communicate through external network. Okay. So we may have to make scheduling decisions in clusters and also in multiprocessor systems. How to do that? How to do it? So one design issue with multiprocessor or cluster systems is we now have processes or threads that try to communicate with each other. So that means there is an interdependency between these processes. So So threads may want to synchronize with each other, and processes may want to communicate with each other through send or receive messages. So any scheduling algorithm should also take this into consideration. So there are two approaches, two well-known approaches. The first approach is called gang scheduling. So here, as the name implies, so we treat all the related processes and threads as a gang, okay? And we schedule each gang at a time. So the scheduling happens between gangs. Okay? So that means threads of all threads of the same process will run at the same time on different cores of multiprocessor machine, okay, on different processors of a multiprocessor machine. Okay? Similarly, processes of the same application or same job, they run on the cluster. They may run on different machines, but they run at the same time. So this is called gang scheduling. So another approach is to use affinity. So here what happens is each thread has a set of processors that are in its affinity set. So that means a thread can only run on the given on this specific set of processors. So this is good because it reduces cache misses. For instance, uh, like operating system uses cache to to improve the performance of memory access. So if a thread always run on the same processor, then the cache will be warm. That way, uh, the thread will have less overhead while doing memory accesses. And one disadvantage is that when there are many threads which have the same set of processors in its affinity, then we may lose fairness because there could be other processors that are free, but we may never schedule there because a thread has affinity towards one processor. Okay, so it has both pros and cons. An example of like scheduler in on real systems is Windows NT. So Windows NT is the first, like one of the first user operating systems uh, that got out. So here there are classes and priorities. So basically, there are two sets of queues. Okay, the one set of queue is real time. The other set of queues is variable queue. So here, in case of real time class, we have 16 static priorities. That means the priorities are assigned once and they never change. Okay? And there is another class of processes which are variable processes, variable class. Here the priorities change. So here there are 16 priorities. However, the priority of the process in the variable class might change. So here we start with the base priority and we decrease or increase based on similar to multi-level queue feedback scheduling that we saw, right? And the scheduling between these classes, so for real-time class, we do round robin within each priority. So we pick the process with highest priority. However, if there are multiple processes with the same priority, we do round robin within a single priority within the highest priority class. For variable class processes, so we do multi-level queue feedback. Okay. So in case of multi-processors, so if there are n processors, so we use n minus 1 to schedule highest priority threads, and we use the last remaining processor for the remaining threads. So that's how Windows NT handles multiple processor machine. Okay, in the next part, we'll be looking into threads.